Hi, Sarah. How are you? Good. I'm doing okay. Thank you. Glad to be home. Yeah. So, hi, everybody. Yeah. I mean, travel is always so stressful, but I had to, just in case I had to get COVID testing. At the airport, they have a lot of locations around the airport to test. I flew out of LAX, and so yeah, just trying to catch up with work. Thank you for asking. Hi, everyone. Thanks for joining today. We'll wait a few minutes. So if you can check out your notes for this week and also your assignment. Yeah, I think now they apply the rules for international flights. But in the future, I think they're going to carry it for all flights. That's what it says on the CDC website. And the testing doesn't take very long, but if you do it at the airport, it costs a little bit of money. If you don't have insurance, you have to pay cash or with your debit card or credit card. So, and there were huge lines. It's so busy. So, but hopefully we'll be able to get all our vaccine taken care of. I think for everyone, they said the latest will be June or July, from what I've read. But our summer schedule is going to be released pretty soon. I'm teaching some non-credit classes for Arduino, Raspberry Pi, and prototyping IoT devices. And I'm also teaching Java and Python again. So it'll be a busy summer. But we're going to do online for the summer. And then for the fall, I think 80% of the classes are going on campus. So it's either hybrid or face-to-face. And then there will be about 20% that's still going to be online. But I think we're going to stream for some part just to transition everybody back. So we'll see how it's all going to work out with room allocation. I'm still finalizing the fall schedule for CIS for Moreno Valley. So, okay, I think we have about a minute. So if you just logged on, please check out Canvas. We are gonna look at the notes. So if you want to download that, and then the assignment, we'll go through that together. I know some students are having exam, so we might not have a big group today. And then I also got result for our extra credit game. I think Juan got first place. And then we got quite a few top winners. We got Rashad, Jose Rocha, Eric Miranda, Scott, Sarah, Daniel Baca. So quite a few of you did really well on the review games. So hopefully you did good on the quiz as well. Okay, so it's 6 o'clock. I'm gonna go ahead and get started. I think some people might pop in a little while. Um, so welcome back. I hope that you were able to do your lab. I graded most of all the labs and all your assignments for this class. This is the only class I'm caught up in grading. I had a little bit of time in between classes just to look through your assignments. So overall, it seems like most of you did well. There were some questions about the lab that, some of you were not able to get your array set up for the last exercise in the last lab. And I wrote back some comments on how to fix that. But overall, everybody did pretty good. So this week we're going to talk about probability, transitioning from permutation and combinatorics. And then we're going to work toward matrix. And we will use matrices in the graphs. So we're moving quite along. So we're in chapter 9 this week. So I'm going to go ahead and go into screen share. And the notes you can find on, let me minimize the people here, in Canvas, so you can download that. And then if you click next, you will be able to find some resources. I added some resources for Markov Chain. We will touch on it a little bit, but there's some tutorial on how to work with matrices. This will be helpful if you wanted to take a look at how to review this for the extra credit that I released this week. So one of the last exercise is going to be an optional exercise. And if you do that, then I'll add the extra credit for you. Okay. I did have some recording in the past, but I'm just going to update that today. So the assignments that we're going to do is going to be Unit 6. And with that said, we're going to touch on the notes and then we're going to start filling out the assignment document. Okay. So, and as I mentioned in this week, we're going to touch on probability. And this is also one of the important chapter transitioning to your project area. Okay, that's fine. Okay, so if you guys have tests and exam for physics class, I understand. If you're not able to participate the entire time, it's okay. We can take care of that when you watch the video, but I will walk everybody through the assignments and you can see that on the video. So when I will release your project pretty soon, probably after week 7, going into week 8. I'm trying to time it so maybe, either that or we can release it after you come back from spring break. So that way you don't have to worry about it during spring break. You do have ample amount of time to find your team. If you decide to work in team, I recommend that you do, and I'll talk about the project and the components and what you need. Okay. So this chapter is the concept of it needs to probably be incorporated in, the option of your project, especially the blackjack game. And so when we're looking at the mathematical theory for probability, it is a way to really present our reasoning in how the event outcome would be. So this gives you a little bit of history on what comes about and how we come up with the probability theory. So Laplace and Pascal give us the foundation in probability. And when we look at the probability, we're just simply trying to predict the ratio in the event that would occur based on what we're given as the possibility and the outcomes. So considering the event based on Laplace theory, that most of our events that where the outcomes would be equal likely. So we would have to take a look at what we would make the assumption based on the outcome given the information in our problem. Now, if you're looking at the event, let's say that we would have one event is represented as a subgroup, which is E1, and we're going to have a union with E2, which gives us the probability of event 1 and probability of event 2. Subtract, right, the intersection of those events, and that would apply the inclusion-exclusion principle. So the best thing to really simulate probability is looking at dice or card games, because that way we can take a look at the set and how that would be represented when we have a specific outcome. So when you're looking at dice, if we're using the standard die or the standard dice, you know that we would have on one dice, we would have 1 through 6 as faces, right? So you can roll either a 1, a 2, a 3, and so on. And the maximum for the dice is going to be face 6. So we have 6 faces on each dice. Now, when we have a pair of dice, right, we would combine the cardinality of each dice. So on dice 1, we have 6 faces. On dice 2, we would have another 6 faces. So we would then take a look at a pair. So in such case, your possibility, your sample space, that's what we call the sample space for both dice would be, there are 6 possibility on each dice, right? Let's say we have a black and a white one. So we would then apply the product rule where we would take 6, multiply it by 6, which gives us 36 possible tosses. So that would become our sample space, 6 times 6, okay? Now, when we're looking at the events where we would have a total is 6, so we would have rolling both dice where we would combine 2 of the faces outcome to be equal to 6. So if we have the first one as 1, we need to get on the second dice as 5 to get a total of 6. So you have a combination of 1 and 5. And then on the second roll, we can do a 2 and a 4. That gives us a 6. And then on the third roll, we can do a 3 and a 3. That gives us a 6. And a 4 and a 2 on the fourth roll. And on the fifth roll, we would have a 5 and a 1. So there are 5 ways that we can roll a sum of 6. So as you notice on the trend here, we going from the black dice, we're increasing 1, 2, 3, 4, 5, right? We cannot roll a 6 because if you roll a 6, there's no dice that would have a face 0. So we have to eliminate the 6. Then on the white dice, we would then decrease. So if we start with the 1 on the black, then the white dice, we would have a 5. And if we have a 2 on the black, we would have a 4 and so on. So as you notice, we would have a decrease of 1 when we're looking at the combination between these dice. So that means that in order to roll a sum of 6, we would have 5 variations, okay, on the 2 dice. So that means that we would take that 5 variations and we divide it by our sample space, which is 36, which gives you the ratio of the event that would give us a sum of 6. Now, if we decided that we need to have a sum of 9, right? Then you can start with 1 dice, that would be 6. The other has to be 3 because 3 plus 6 gives us 9. And then as you increase for the black, so here, if we wanted to roll a 5, if we roll a 5 on the white, then we have to roll a 4 on the black to give us a 9. And 5 on the black, then 4 on the white, 6 on the black, and 3 on the white. So now that would be the total number of variations that we can roll to get a sum of 9. Okay, so with that, we would take the 4 variations and we divide it by our sample space, which we found in the first exercise here. That gives us 4/36, or you can reduce that down to the ratio of 1/9. So in order to get a sum of 9, I have to roll at least 1/9 tries, right? To get a sum of 9, okay? So if you're looking at crap games at casinos, right? Or if you just play it with your friends, you can start looking at the ratio or the probability of how you would be able to get a certain score when you have these dices, okay? Any question with this so far? Okay, so these exercises just simply show you the combination or the variations in how we would throw the dice to get a certain sum as a value, okay? Now, what if we wanted to have a range? What if we want to roll a number that's higher than 8? Okay, we know that 9 is higher than 8, 10 is higher than 8, 11 is higher than 8, and 12 is higher than 8. And 12 is the maximum because if you roll 6 and a 6, right, then that's a 12, okay, and it stops there. So first we have to examine the sum of 9 that will be higher than 8, and we previously done that. So we have 4 ways to roll a sum of 9. Then we would evaluate the number of ways where we would roll a sum of 10. So we can do a 4 and a 6, a 5 and a 5, and a 6 and a 4. So 3 ways. Okay. Then next we have to evaluate the variations that we can roll in a sum of 11. So there are 2 ways, a 5 and a 6, and a 6 and a 5. And you can start seeing the trend. So when we go from 9 to 10, we reduce the combination by 1. And from 10 to 11, we then again reduce the combination by 1. So for the sum of 11, we have 2 variations. And then lastly, we have to take a look at 12, right? Which gives us 1 way, okay? Which is 6 and 6, and that's the only possibility to roll a 12, a sum of 12. So once you have all of that, right, starting from 9, and then we go to 10, 11, and 12, then we add them up, okay? So I have 4 for 9, 3 for 10, 2 for 11, and 1 for 12. Once I add these up, I should have 10, right, ways that I can roll higher than 8. So that would give me the probability of 10/36, and 36 is our sample space to start, as there would be 6 faces in each dice. So we multiply 6 by 6 gives us 36. So our ratio, our probability for rolling higher than 8 as a sum would be 10/36, or you can reduce that down to 5/18. Okay. Now you will see example or exercises like this on quiz and exam in the future. So it would give you a scenario and then you have to determine the probability based on what's given to you as sample space, okay, in the problem, and then you have to determine how likely that event would occur. So for us, we have 5/18 or 10/36 rule that would give you higher than 8, okay? Any question with this? Okay, let's take a look at a few more and then we'll do the assignments. So what if we wanted to roll a 7 or an 11? okay, then what we have to do is we have to look at the ways, the variations in how we would roll an 11. And we talked about that in the previous exercise. We can do a 5 and a 6 and a 6 and a 5. So there are two ways that we can roll a sum of 11. And we then have to take a look at how many variations we can get a sum of 7. So we can start with 1 on the black dice and 6 on the white. That gives us 7. 2 on the black, 5 on the white, 3 on the black, 4 on the white, 4 on the black, 3 on the white, 5 on the black, and 2 on the white, 6 on the black, and 1 on the white. So that gives us 6 variations or 6 combinations where we can get a sum of 7. Wait, we're not done, right? It's asking for both, one or the other. So that means that we have to take the number of combinations of 11 and the combinations of the sum of 7, and we add them. So 2 plus 6 gives us 8, and we divide that by 36, which is our sample space. So 8 over 36 is our ratio, and we can reduce that down to 2/9. Okay? So to roll a 7 or 11, we would have 8 out of 36 rolls or 2 out of 9. Okay, so this is going to be our probability, which is the ratio. Okay. Now, if you wanted to narrow it down to percentage, you simply take this and divide it 2 divided by 9, and you get a decimal point, and then multiply it by 100 to give you the percentage. Okay. Now, what if we wanted to roll the same number, right, for both of our dice, like a pair? So we would have a 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, a 5 and a 5, and a 6 and a 6. So there are 6 ways, right? And it stops there because the maximum, the highest face on our dice is 6. So there are 6 ways that we can get the matching numbers. So then we would take the 6 divided by 36, which gives us 1/6, or 6 over 36. Reduce that down to 1/6. So 1 out of 6 roll would likely give you a pair. Okay. Now for the next exercise, if we wanted to have a numbers that are 3 and 4, 4 and 3. Okay. So we can do a 3 and a 3, a 4 and a 4. So that gives us 2 ways that you would have a 3 and 4. So that gives us 2 out of 36, or reduced down to 1 out of 18. So we can say that we can have 1 out of 18 rolls that would give us a 3 and a 4. Okay. Now, if we wanted to do snake eyes, and snake eyes is a nickname for a pair of 1, there's only one possibility, because in each dice, you only have one face. That's going to have a 1. So in order to roll that pair, right, that's going to be 1 out of the 36. Okay. So if you're looking at any pair, if I'm looking at a pair of 2, that's only going to be one way. So, or a pair of 3, right? So that will be 1 out of 36 try. Okay. So here gives you some different examples on how you can look at the probability with dice. So let's work on our first exercise. Okay. So in the assignments, you can refer to the notes and solve. Or if you already know how to do this, you can just simply the first thing that you need to do when you're looking at probability is to calculate your sample space, right? And in this case, we use the product rule. We talked about that last time, the last couple of weeks. So since each dice has 6 phase each, and we're using 2, we would take 6 times 6 gives us 36. So if we're using a pair of dice, a red and a black, right? What is our sample space? And if it's standard dice, 6 phase, so 6 times 6 gives you 36. And you don't have to write this down. I just write it down so you can see the explanation. If you wish to do that for your notes and your assignments, that will be okay too. Okay. So your sample size is going to be 36. And if we're using the same pair of dice from the first question, we wanted to roll a sum of 7 for 2A. Okay. And the chart is there just to help you visualize, but if you don't want to use the chart, you can just type out the combination so you can count it. So I start with the 1 on the red. I need to get a 6 to get a 7 total. Then I move to the 2. So what helps me in tracking is I keep the number organized across, and I would increment by 1 each time so I can track it. Okay, so the second combination, I would have a 2. Then for the black, I need to have a 5 if the red is 2. Then next, I would have the third combination. I have a 3 on the red and then 4 on the black. For combo 4, I would have a 4 on the red, right? We move from 3 to 4. And then that means I need to have a 3 on the black to have a sum of 7. And I would continue to do that for combination 5. I move over to 5 on the red. That means I have to have a 2 for the black to have the 7 total. And then the next one, combination 6, I would end up with 6 as the face on the red. Then I need to have a 1 on the black. And so you can see the trend, we increase by 1 as we look at the combination, and we decrease by 1 for the other dice, right, as we go through the combination. So when you count all of these combinations, you have a total of 6 combination or variations in how you roll the dice to yield a sum of 7. Okay. So the next step in solving these type of problem after we determine the sample space is to look at the number of combinations or variations where we can yield a specific sum. Then after we have the combinations, then we can take that number and we divide it by our sample space, which is 36. So we took 6 in the combination divided by 36, which gives us 1/6 as a reduced ratio. And if you wanted to really calculate it out to a percentage, you can take 1 divided by 6, which gives you 0.1667 roughly, right? And if you multiply it by 100, you should get about 16.67%. Okay. So if you think about a game, like a casino game, right? With the bets, if you wanted to hit a sum of 7, let's say that with that, they might double your wager, then you have about less than 20% to be able to hit a sum of 7. Okay. So that means that out of 6 roll, we're going to get 1 roll that's going to hit a 7 sum. Okay. So here you can calculate your probability. And so for the test answer, right, the options where you can choose your answer, I would I would keep it as a ratio. I would not put decimal in because, you know, but if you wanted, if you're curious, you can calculate that out to decimal and multiply it so you can see the percentage. Okay. Now, why is this important for computer science students, right? In the case, many of you are interested in creating games, right? And when you're using these app games on your phone or on a website, like if you're looking at like those gambling websites, depending on the state, whether it's legal or not, right? All of this is already predetermined, like how you play with the computer, how they program it with artificial intelligence so the computer can play against you, right? And in a lot of cases, when you go into a casino, casino machines already have these programs, right? And you know that the house always win, but what's the probability of a person winning against the house, right? Like in the case of jackpot or in any form of game, all of this is already built into the discrete part of the programming side. So we have to mathematically determine and solve this problem and then translate that into codes to be able to say, okay, if we create a program that the house always win, we have to take a look at the probability behind it. Okay. Or if we create a program that's always going to be favoring the user, right? We have to determine the probability behind that. Or in some cases, if you're looking at like a card guessing game, which is what you see on projects, right? Our project, then you have to determine the probability of how the card games would be the turnout based on what the user is dealt. Okay. So any question with 2, A and B? All right. No questions. Let's take a look at number 3. So we would now need to determine our probability for rolling less than 7 as a sum. So that means that we have to determine the sum of 6, 5, 4, 3, and 2. Okay. So I'm going to illustrate the 6 one in the table, and then we would write down for each of the sum because it's just going to be reduced by 1. So that's easy. So first we're going to start with the highest number based on the given criteria, right? Less than 7, the highest is going to be 6. So we would look at the combination 1 and 5 for 6, 2 and 4, 3 and 3, 4 and 2, and 5 and 1. And we drop out the 6 because 6 is too high and there's no face 0, right? So we cannot include face 6. So 1, 5, 2, 6, 3, 3, 4, 2, and 5, 1. So that gives us 5 combinations for the sum of 6. Okay. So our probability is going to be 5 over 36, or if you wanted to look at the percentage, that will be a little bit under 14%. Okay. We're not done. So we know that there's 5 combinations for 6. Then we have to evaluate the sum of 5 combinations. Okay. So we can do a 1 and 4, 2 and 3, 3 and 2, 4 and 1. And just like the example exercise, you know it's going to be reduced by 1 when we go 1 less. So that gives us 4 combinations to get a sum of 5. So that means that we have 4 over 36 or 1/9. And you can leave it like this or this. Next, we would then look at the combinations for the sum of 4. And so going from 5 to 4, we should predict that it's 1 less, right? So we can see the combination with 1 and 3, 2 and 2, and 3 and 1, which gives us 3 combinations, 1 less like we predicted. So that means that the probability would be 3 divided by 36, or if you reduce that, that would be 1 out of 12 rolls to get a sum of 4. Then again, we would continue for the combination for the sum of 3. And sum of 3, it's going to be 1 less than the last round, so 1 and 2 and 2 and 1. Pretty simple. That gives us 2 combinations. So 2 divided by 36, or we can reduce that down to 118. Then we got to go one more round. We have to look at the combination for the sum of 2, and that's easy because there's only going to be one combination, which is 1 and 1. The pair of 1 is going to give us the sum of 2. So for the sum of 2, it's 1 out of 36 probability. So once we have each of the combination for the sum that will be less than 7, going from 6 all the way down to 2, then we add them up. So you start with the sum of 6, which is 5, then we move to 5, then we move to 4, then we move to, and so on. So you have 5 plus 4 plus 3 plus 2 plus 1, which gives us a total of 15 combinations for sum that is less than 7. Then we would take this 15 and we divide it by our sample space, which is 36. So 15 divided by 36, we can reduce that down to 513. And if you wanted to know the percentage, that would be, so you take the ratio and multiply it by 100, you would get 41.67% to get less than 7 as a sum. Okay. So this is really the result, the highlighted in yellow. But in order to find it, we have to look at each of the sum combination, add them up, take that divided by the sample space to get the ratio. And you will likely see question like this on quiz and exam once again. Because if you have a 6 on one face, there's no face 0. The smallest face on a dice is a 1. You have 1, 2, 3, 4, 5, 6. So the highest is 6 and the lowest is 1. So if you roll a 6, there's no, the second dice, it has to be a 1, right? And that will be over, that will be at 7. It won't be 6. So no face 0. So you cannot include 6. Okay. And if you're not sure, you can take a look at the actual physical dice, right? If you have it, or if you can look at a picture of it online, you can see there's no face 0. Now, in some game, you have like dice that have higher than, it's not a standard dice where it would have higher than 6 faces, then you have to look at, how many faces it has to really get the sample size, right? But this is a standard dice, so it goes from 1 through 6. There's no face 0. So All right. The next question, question 4, asks you, what is the probability of rolling a dice to result in a snake eye, 1 on each dice, right? We want a 1 and a 1, a pair. So we know that there's only one way, okay? One way to get a 1 and a 1. There's only one face that has a 1 and another face on the second dice that has a 1. So there's only one way to have that pair. So that will be 1 out of 36, right? And if you wanted to look at the decimal, you do the division. So the probability in that in percentage, right, that will be about less than 3% to get a pair. So if you look at casino game where they say if you roll a pair, right, you will get, let's say, quadruple the wager. Well, look at the probability behind that. When it's low is when you can actually win big, right? And they know that. Okay. So one way to get snake eye or a pair of ones. Okay, so now what we want is we want to check for probability that one dice is higher than the other. Like if I roll a 1, right, on the black dice, I have to roll a 2 on the second one to get the points. Okay, so it's always going to be higher. Okay, so if we have the red as 1, right, then we can't count that because we would start with a 2 on the red and a 1 on the black, because if the red needs to be higher in our game here. Okay, because 1, there's nothing below 1. 1 is the lowest, so you cannot have the black as 0. There's no 0 face, right? So we can't count that combination. So the red has to be a minimum of 2 because black needs to be lower, right? Because it says that the red dice has a higher result than the black. So if I roll 2 on the red, then I would have 1 on the black. So that's the first combination. If I roll a 3 on a red, then I can have 2 combination. I can do a 3 and a 1 and a 3 and a 2. So I would have 2 combinations there. If I roll a 4 on a red, I can have 1, 2, 3, because those are lower than 4. Then I have 3 combinations there. If I roll a 5 on the red, I would have 1, 2, 3, 4 combinations. And then lastly, if I roll a 6 on the red, I would have 1, 2, 3, 4, and 5 combinations. Okay. As long as the red is higher, we can include the other ones. Okay, so we see that as we increase on the red face, we would have more combinations with the black. Okay, give me 1 second. So when you look at those problems, you have to look at what the question is asking, and then you need to determine the combinations, right, based on what the question is asking. Okay. So once we have the combinations established, okay, then we add them up, starting with 1 for the first combo, then 2 for 2 combinations when we get a 3 on the red. So 1, 2, 3, 4, 5 as we go across. Okay. That gives us 15 total combinations in which red dice is higher than the black dice. And we would then take that 15 and we divide it by 36, which gives us the probability we can reduce that down to 512 as a ratio. Or if you actually take 5 divided by 12, you get 0.4167, multiply it by 100 to get the percentage. So the percentage of an individual that would roll one dice higher than the other would be about less than 42%. Okay, so this one is a little bit more complex than the other one, but you have to think logically about this, right? You have to think about, okay, if I roll one dice at this number, what would be my combination for the other dice? And how many combinations will I get? So the hardest part, I think, to solve this problem is to determine the combinations. Once you have that, you just take that divided by your sample space and you have your probability. Okay. So the chart is there just to help you visualize it so you can track it. But if you don't have the chart for the test, right, you can simply write down the variations of your outcome and then take those combinations and add them up in the case of a question like this, and then divide it by your sample space and you have your answer. Any question with question 5? Okay, all right. I'm glad that you're getting it. So this one, this is one of my favorite chapter after combinatorics because you can see like every time that you watch a game show from now on, you're gonna say, oh, I already know, right? Why that person did not win the car, or why that person did not win, $50,000 or $1 million. In the game show where people open suitcase and so when you look at the options when they open the suitcase and they're trying to save the last one for the $1 million or whatnot, right? You can start determining, okay, why is the banker giving them more higher wager? Because the probability is lower, right? It's harder for them to win. Or I mean, the higher is because they have a higher chance to win and they want to buy them out. So a lot of the times we can see this in the real world scenario. And when you're looking at applications, right, from analytics to, things like the casino use or, a web app that's giving you the game, then you can start thinking about how you would employ discrete structure when you write that type of program. All right. Okay, so now we're going to do the next one. We want to roll even. Okay, so for question 6, it asks you for the probability to roll even number on both dice. Okay, so think about the even number. Okay, if both dice come up even, the sum will be even, right? Like a 2 plus a 2 is a 4. If I have a 2 and a 1, that's an odd. That's a no-go, right? That's no good. So both dice have to be even in order to give you an even output. Okay, so when we look at the combination, we can do a 2 and a 2. Okay, a 2 and a 4, a 2 and a 6. Okay, that gives me even outcome. Then we can have a 4 and a 2 combination, a 4 and a 4, a 4 and a 6, a 6 and a 2, a 6 and a 4, and a 6 and a 6, and we stop because there's only 6 faces in each dice, right? So what I did was I start with the lowest value, right, on one dice, and I look at the combination for those, and then I move to the next value. And again, I look at the combination for those to get an even sum. And then I go to the next number. And 6 is where we stop because there's no higher value. Then once we establish the combinations, we see that there are 9 ways in which both dice have even numbers to give us even sum. So we would take that 9 and divide it by 36, which gives us 1/4 or 25%. Okay. Okay. Now, if you have a question that asks for an odd number, right? Then you think about the combinations of your dice to yield an odd sum, like a 1 and a 3, a 3 and a 1, a 1 and a 5, and so on. So it's the same concept that would apply to the odd sum as what you would be. So the dice have to be odd in order to get the odd sum. So you would set up the combination and then total them up, and then take that, the total combination divided by the sample space, and you would have your answer. Okay, any question with number 6? Okay, so now what we're gonna do is we are gonna move, we're gonna transition from dice, we're gonna go into cards. Okay. And in most casino, they use multiple decks, right? But when you play cards with your friends, or when you're playing poker, things like that, right? I know that in my classes for Java and Python, I asked for those of you who want a challenge to do a poker game. Discrete knowledge helps when you're working with these type of games, okay? Because you would then be able to evaluate the winning and how you pair the combinations in the case where if you're looking at blackjack, or with the poker, the options are, depending on the type of poker, but you have certain rank in the winning tier for poker. It's a little harder as compared to blackjack. So if you're looking at card games, sometimes card games can be very detailed in how you would write that program. So you have to really break it up into subtasks and look at how you would incorporate, right? The conditions in how it would win, and be able to compare the winning. Okay, so we'll touch on the project later on, as we move along, and you can pick and choose what kind of project you wanted to do for this class. And of course, we have to apply to the discrete portion of the math portion of it to really solve the problem. That's the point. Okay, so let's flip back to the notes. And after the example for the dice, it goes into the cards in exercise 9.22. So your standard deck of cards, like the bicycle card, that the playing cards, right? Remove the joker is 52. Okay, we don't use joker in a standard deck. So when you're looking at casino, when they're using 4 decks or 3 decks, and they always swap the decks, right? So if you look at the shuffler at the table, if you ever pay attention, in that they would stack the various decks. And the more number of decks that they use, there will be a higher chance for the player to win compared to a single deck. Okay, so and we'll come back to that when we talk about blackjack game rules down the line. So when you're looking at a single deck, there are 52 cards, right? And just to kind of break it down, so you have 52 cards. You have 4 suits, okay? You got spade, right? Clubs, diamond, and what hearts, okay? Then the first 2 right here are black, okay? And then the last 2 are red. Okay, so the diamond, the hearts are the red, and the spade and the club are black. Okay, so 50% of the deck is red and 50% is black. Okay, then in each of the suits, so each suit you have, if we count the ace as 1, then we have from 1 through 10 as regular cards. Now, then we count the jack, the queen, and the king as face cards. There, you would have, each suit would have 3 face cards. Now, depending on the game, sometime in certain game, they would count the ace as a face card. Okay, but for the sake of this exercise, we're gonna count jack, queen, and king as face cards. And ace through 10 will be just regular cards. That will be just number cards. Okay. So if you count up the number of cards in each suit, okay, how many do you have? Okay. So you kind of have to dissect it and look at like how each of the suit is broken down and how many suits are there in the cards in order to really start working through these problems, right? So our sample space is going to be 52 because this is a 52 card deck, right? So if I'm using 2 decks, then you would take that just like what you did with the dice, right? Okay. So each card is a possible event and our sample space is 52. Now the next exercise, the next example, it asks you the probability of each of these events. B, if the card is a face card. So if I have a deck spread out and if I'm pulling a card, right, what's the likely that that card is gonna, what's the likely chance that that card is gonna be a queen, a jack, or a king? Okay. So we then have to take a look at the number of face cards that's in that deck. Earlier, we mentioned that there are 3 face cards in each suit, and there are 4 suits. So that means that you have 12 face cards, okay, in a deck. 4 jacks, 4 queens, and 4 kings. So the probability of me getting a face card in a single deck is 12 out of 52, and you can reduce that down to 3 out of 13. Okay, so out of 13 try, I will likely get 3 of those tries will be my face cards. Then for the next question, it asks me if the card is a black card, right? We know that half of the suits, the spades and the clubs are black. The diamonds and the hearts are red. So half of the cards are black. So the probability of that is going to be half of 52. Okay. So half. Now I need to determine if the card is a heart, right? It could be any, it could be 2 of hearts, queen of hearts, any hearts. We know that in each suit we mentioned earlier, we have 1 through 10 and jack, queen, and king. So there are how many cards? 13, right? So 13 cards are going to be hearts. So that will be 13 out of 52, or reduce that down Okay. I think I'm off on this right here. We'll just leave it like this. All right, now we need to determine if the card is a queen. There are 4 queens because there are 4 suits, and each suit has a queen, a king, and a jack, right? So there are 4 queens in a single deck. So that means that 4 divided by 52, which gives me 1 out of 13 try, I'm going to get a queen. Okay. So that will be a queen. And then for F, if the card is the number between 2 through 10. Okay. So when you're looking at this set, the cardinality of this is 9, right? The total number of cards between 3 to 10 total is 9. There are 4 suits, so we would take 4 times 9, which gives you 36 cards in any suits that will fall into 2 through 10. Okay. So we would then take 36 divided by 52. So if I need to pull a card between 2 through 10 in any suits, I will likely get 9 successful outcome out of 13 tries. Now, if we wanted to get 1 ace of spades, right? Let's say you need that ace of spades to win the game. Well, there's only going to be 1 out of 52 if we're using a single deck. Okay, 1 ace of heart, 1 ace of spades, 1 ace of diamond. There's only 1 ace of that suit. 1 out of 52. Now, since we did not include the joker because the joker is not part of that sample space, so the probability of that is going to be 0. We don't include joker in the standard deck. Okay. All right. Any question with the examples? So let's take a look at our assignment, number 7. Give me 1 second. Sorry, my dog has cancer and he was outside for a little bit by himself. I was worried that he falls down or something. Okay. If a single card is drawn from a deck of 52, what is the probability of this event? So earlier we touched on looking at the face card, right? So here it asks for one of the face card, which is a queen. There are 4 queens in a deck: queen of hearts, diamonds, spades, and clubs. So there are 4 queens. So if we need to pull a queen from a deck, then that will be 4 out of 52, which is like under 8%. Okay, so we would have 4 successful outcome out of the 52. Okay, then next we're gonna have to check to see if the card is a red card. Okay, so we can have red face card, I'm sorry, heart, and then we can have a diamond. Okay, so for the heart, we would have jack, queen, and king, and diamond, we can have jack, queen, and king. So that gives us 6 total. And those are the only 2 suits that are red. So 6 out of 52, which gives us like 11.5, less than 12%. Okay. So 6 successful outcome out of 52. Then for the next question, it asks us to get cards that would have the same suit. Okay. So there are 13 cards in each suit. So we would take that 13 divided by 52, which gives us 25%. Okay. And then what if we wanted to get a card that has an even number? Wouldn't it be 12 out of 51 since you have gotten the card first? So the way that you look at it is the first attempt is going to be 13 out of 52, right? You pull, and then because there are 13, we are not reducing the combinations or the actual number because there are 13 exact suit and it's static, it doesn't change. 13 in a suit. Okay. Now, so if you're pulling one card first, that will be in order to get that within that one suit, it's going to be 13 out of 52. But in the second round, you are aiming in the right direction, is that we have to permutate for the second card to be one less. Okay, so that will be 12 out of 51 for the second card to be in the same suit as the first one. So yes, the question is lacking a little bit, but I think it's really intended for the first pull for the card in that suit. So if we say that, we have to pull clubs and clubs, right? Then the first round is 13 out of 52. The second round is 12 out of 51. Okay, we want a card to be an even number, right? Like a 2, a 4, a 6, a 10, etc. So that will be 5 out of the 13. Because if you're looking at 2, 4, 6, 8, right? 10, that's 5. And there are 13 per suit. So 5 out of 13 per suit. And then if you're looking at all suits, that would be 5 times 4, which gives you 20. And all cards is 52. Okay. Any question with these? So likely you will have questions like this on exam and quiz, right? It would ask you for the right options that you need to select based on the given scenario of cards, suits, and such. Okay. So now I'm going to flip back to the notes. And then we're going to take a look at the next example. In this one, it talks about the urns that's going to contain a 15 red and 10 blue. And you need to pick one ball out. Okay. So like all the other questions or all the other exercises and example, we need to start establishing the sample space, right? So we have 15 red and 10 blue. So that gives us 25 total for our sample space. Okay. And if we start numbering each of the ball, right, and we can pull out specific number, then we can look to see the probability. So after we establish a sample space based on the given scenario, then what we need to do is we need to start looking at how to draw just red, one ball that would be red. Okay. So there are 15 that are red. That means that we have to have 15 draw at least in order to get a red. Okay, so 15 out of 25 would be red. And we can reduce that to 3/5. Now, if we wanted to draw the blue, look at the blue, we have 10. So that will be 10 out of 25. Or we can reduce that to 2/5 for the blue. Now, in the case if we want to draw a blue and a red, then you just add them, right? Okay. And they are complementary, as you can see. 3/5 plus 2/5 is 1. Okay. Now, when you're looking, going back to what we talked about last week with the choose, right? The choice that you make out of the cardinality out of n, you choose R out of n. Okay. When we talked about permutations and combinations. So in this case, when we're looking at the draws, now if the balls are drawn once, that means that when they're drawn, they're removed from the urns, we don't put it back, it becomes a permutation. There's no repetition, okay? Because in combination, we can reuse that number. So when we have to choose 3 out of 25, we're gonna start with 25, take one out, then we have 24, take another one out, then we have 23. Then we would take these, multiply them, 25, 24, 23, divided by 3 times 2 times 1, because we start with selecting 3, right? A factorial of 3. So a factorial of 3 down here. So that gives us 2300. Okay. That's if we wanted to draw 3 at once, and each time, right, they're not going to be put back into the container, the urn. Okay. For the probability of all of the balls are going to be red, when we look at that, we look at 15 of them are red, not 25, right? 15 only are reds, and we're going to choose 3 out of 15. So that gives you 15 times 14 times 13 divided by 3 times 2 times 1, which gives you 455 ways to choose 3 red balls. Right, so the probability would be 455 divided by 2300 for the total, which gives you 91 over 460. Okay, so what are we establishing here? First, we, just like all the other one, we have to start looking at the sample size of how we would select 3 out of the urn with blue and red. Okay, which gives us this. Then we would focus on only 3 of them are going to be red. Okay, and that is 455 ways. Then we take that divided by the total 3 draw with both type of balls in the urn. which gives us the probability of the 3 are red. Now, what if we're looking at 2 are going to be red and 1 would be blue? Then we would choose 2 out of 15 for red, 15 times 14 divided by 2 times 1, which gives you 105 ways to choose the red. Okay, and there would be 10 ways to choose 1 that would be blue. Okay, because there are 10 blue ones. Then we would take 105 times 10 because now we have to make consecutive choices. So we would apply the product rule, which gives us 1050 ways to choose 2 red and 1 blue. Okay, we're not done there. After we have the combinations or the selection choices, then we would take that and divide it by the total sample space that we established earlier for the 3 balls, any balls. Then we would have 21 over 46 to choose 2 red and 1 blue. Okay, so this is a little bit more complex where we have to take a look at, the red set, the blue, multiply them, and then get the probability from the variations like what we practiced earlier with the earlier exercises. Okay. So now, if we take a look at how we would apply this with the experiment, if we have the same urn with the same type of balls in there, and we wanted to draw 3 sequentially, this is order, okay? But at the same time, we put it back, we would return it. So we don't really reduce the number of balls as we draw them out, okay? So then we would remain at 25 in our sample space, but since there's 3 draw, we would take the 25 and raise it to the 3rd power, right, for 3 draws. Then we would get 15,625 sequences where 3 would be drawn, and we would put the ball back. Okay, so this is different than the last one in that in the last one, as you take out the ball, you remove it from the urn and it doesn't go back. Okay, in this one, we put it back so the 25 stays the same. Okay. Now, in this one, then we would draw 3 red, right? Every time we draw, we put it back. So you would take 15 and raise it to the 3rd power because there are 3 draws, which gives you 3,375 sequences for 3 red balls, but returning the ball each time. Then the probability of this would be 3,375, right, divided by 15,625, okay, which is 27 over 125. Then in the next one, we would select 2 balls that would be red and 1 is blue, okay? And it says that there are 3 positions for the blue and there are 10 that can go into this position, right? We can plug in any of the 10 because we are able to put them back each time. There are 15 to the 2nd power for the red because there's 2 draw for red. Okay, so once you calculate that, you have 225 sequences for the 2 red. And then we would take 3 times 10 times 15 to the 2nd to give us 6,750 outcomes. Okay. Why are we multiplying by 3? Because there are 3 positions, because they are sequence, they are individual number. So 3 times 10 is going to take care of the blue, and 15 to the second power is going to take care of the red. Okay. So once you have 6,750, you would take that and you would divide it by 15,625, which gives you 36 over 125 as a ratio or a probability. All right, so let's try our exercise now. So for question A, it asks you, it tells you that there are 10 balls, number 1 through 10 in a bag. What's the probability of drawing a number 8 ball in a single draw? So we know that there are 10 possible outcomes and only going to be one successful outcome, right? There are 10 ball and you're going to pick one out. There's only one 8 ball, so that's 1 out of 10. So for 8A, it's 1 out of 10. Then we would look at, for 8B, the probability of drawing a number 8 ball in 3 draws, if the ball is always going to be returned to the bag for the next selection. So once we take it out, we can put it back, right? And so in this one, the 10 stays the same. So we would apply the product law. So we would then have 10 to the third because there are 3 draws, which gives you 1,000 possible outcomes. That's your sample space. Now, we would then apply the inclusion-exclusion principle. We would look at, if we take one out, then that gives us 9 to the third outcomes that do not have that number 8 ball in the draw. Okay. So once we look at what would be the value that does not include the 8 ball for the 3 draws, then we would take the possible outcome and we subtract the outcome that does not have the 8 ball, which leaves us 271 outcomes that does contain the outcomes that do contain the number 8 ball, which is 271 over 1,000. Okay. So in this one, what you're doing is first you have to establish what is your sample space or the possible outcome of the 3 draws based on the given number of balls in the bag. And then the next step is to look at what is the outcome that does not include the 8 ball for the 3 draws. Once you have that, you would take the possible outcome, subtract the outcome that does not include the 8 ball, which gives you 271, or the outcome that contain the number 8. Then you take this number and you divide it by the sample space, which gives you the probability. So in this exercise, we apply inclusion-exclusion principle to determine the probability for the 8 ball in 3 draws. Any question with this? Okay. Then for question C, we look at the probability for drawing a number 8 in 3 draws if the balls are not returned to the bag after each selection. So once I take the ball out, it doesn't get returned. Okay, so we don't reuse that ball. So first we have to take a look at the sample space, the possible outcomes. So I started with 10 ball, take one out, then I multiply it by 9 because it's one less. Take one out, then I multiply it by 8 because it's again one less. And that gives us 3 draw. So when you multiply everything together, it gives you 720 possible outcomes. Then we're going to have to look at what we need to exclude, which is the possible outcome that does not contain the 8 ball in the 3 draw when we don't return the ball. So 9, right, times 8 times 7, because it's one less, right? Once we take the first one out, it's going to be one less. That's not going to be an 8. And then again, one less, that's not going to be an 8. And then one less, it's not going to be an 8. So we stop there. So 9 times 8 times 7, which gives us 504 possible outcomes that do not include the 8 in the 3 draws. So once we have what to exclude, we would subtract. So we would take 720, subtract 504, which gives you 216 outcome that does include the 8. Then we would take that 216 divided by our sample space, which is 720, which gives you 310. Three over 10. So out of the 10, right, we can have 3 that would be 8. That would have the 8 ball. Okay, any question with this one? All right, now next we're gonna try to solve it for a specific draw, like a specific ball that we're gonna get out of the bag. We wanted to determine the probability of drawing numbers 9, 5, and 2 in 3 draws if the ball drawn are returned to the bag for the next selection. So we take the ball out, then we check the number, then we put it back. But we want the number 9, 5, and 2. Okay. So we would look at the combination of 9, 5, and 2, like how we did with the dice. Okay, so I can have 9, 5, and 2, 9, 2, and 5. Okay, here. 5, 9, and 2, 5, 2, 9, 2, 5, 9, and 2, 9, 5, which gives me 6 successful outcomes out of 1,000. Because why are you using 1,000? Because it's 10 to the third as we replace the ball every single time. So our probability of getting the variations for 9, 5, and 2 in our draws would be 6 out of 1,000, which is 3 out of 500 as we reduce that ratio. Okay. So to solve D, you simply just start with determining the variations of achieving those numbers, 952 in combinations. Then once you have the combination number, then you would take that and divide it by your sample space, which is 1,000, and you would have your probability. Then for E, we would look at the probability of drawing 952 in any order. But in this one, we're not returning the ball for the next selection. So earlier, right, we mentioned that there are 6 successful outcomes in exercise D, right? These are the combinations in any order. So we know that there's 6 successful outcomes. But in this one, our sample space is 720, right? We achieved that from here, from question C. So we then have 6 divided by 720, which gives us 1/120. So definitely much smaller sample space when you don't put the ball back. Okay. Compared to question D, you put the ball back, so your sample space is much larger, which means that your probability is lower compared to if you remove the ball and don't put it back. Your probability would be higher. Questions? Okay, I'll leave it here for a little bit more and then we'll move on to the next part, which is we're going to talk about diagram and Markov. Okay, so make sure that we know how to solve these. Okay, you will have also another quiz review down the line, but I do have a final review assignments to kind of go back and help you review. However, you should expect this on quiz and exam. Okay, next part. So here it talks a little bit about tossing coins. So you can also check that one out. Looking at bits and bytes. So next we're going to talk about Bayes theorem, which is the conditional probability using Bayes theorem. And Bayes theorem is a way to find the probability when we know that there's other probability that's for certain. Okay. So in the shown example, it shows you that first we know that how often A happens, given that B happens. So we would write the probability of A or B. And if we know how often B happens, we would be able to have given a certain A happens. So in the example that's used in the book is that, it talks about fire and smoke. So if you know for sure, right, that there is smoke, then you can look at the probability that a fire occurs, right? So now for the third point, it says how likely of A is on its own would be written as probability of A, and how likely of B is on its own is written at probability of B. Okay, so the way we look at this is the probability of A or B, that would be probability of A times probability of A or B divided by probability of B. And when we apply this to an example for fire and smoke, we look at the probability of fire times probability of smoke or fire divided by probability of smoke, right? We would get the percentage or the ratio to represent fire or smoke. So now given Bayes theorem, right? If you're looking at like the game show, so if you're the contestant at the game show and there's 3 doors, one door leads to a new car, the other 2 door leads to a lemon, nothing, not a prize. If you're able to find the door that leads to the car, then you win a car. And you're told to select one door but not open it. So when you pick door number 1, and at this point, the host would then show you the other 2 door, which reveals a lemon. Then the host asks you, do you want to switch? Right? What should you do? So we know that the car, right, is behind door A, or the first door. Now, if the host opens one of the other 2 doors that leads to the lemons, in this case, you want to stay. Okay. But most people intuitively, they would want to switch because they think that they would have a higher chance by switching. Now, if the car is behind door B, or the second door, then the host will open door C. And in this case, your response is to switch. That will be correct. Okay. Now, so you can see the scenario, and this actually was something that was established by looking at game shows, right? And I put some links on to the canvas so you can look at different game show scenario, like what we talked about before. Okay. Now, if the car is behind the third door, door C, then the host will open door B. The correct response would be that you are to switch. So 2 out of the 3 equal likely cases that you should switch. This means that you are more likely to win the car if you switch. Okay. So now when you watch those game show, you can try to evaluate the probability of someone winning the prize behind one of the 3 doors, right? Whether they should stay or switch. So with the conditional probability, this is a way that we measure the probability of an event occurring given another event that has occurred. Some event can be independent, meaning that the event does not affect other events, like tossing a coin. Or some event can be dependent, okay? Which means that it can be affected by the previous event. So now when we go back and we take a look at, in the case where an example similar to what we've done, where we have 2 blue, 3 red marbles in the bag, and the chances of getting the blue marble, that will be 2 out of 5. But after you take one out, does that change? Now, if you get the red before, then the chance of the blue marble is going to be 2 in 4, right? Because we reduce by 1. But if you take the blue out, the chance of the blue marble next is going to be 1 in 4. So in this case, we see that there's dependency. Okay. And if you wanted to take a look, right, you can take a look how it branches off, like from the beginning. And in any case, these branches would be add up to be 1, right? 2 out of 5 times plus 3 out of 5, that's going to give you 1. And then from here, that it would affect the outcome of the next branches, 1 over 4 plus 3 over 4, because now we have 1 less, right? And then from this branch, it's also going to affect this options. Okay. And this is what we call the conditional probability. And in this case, we have dependency. Okay. So now, right, where do you really see Bayes' theorem being used? In statistics. Statistics is heavily used in data science, in analysis of your data sets, in machine learning, in information retrieval, and diverse applications in science and engineering. So endless, right? And the door information, right? The game show stuff that was shown earlier. Here's the Monty Hall paradox with Bayes' theorem. Okay. So if you wanted to look through on how you would calculate the probability, you can take a look at that. If we select one door and they show us the other door, right? What is the probability? Should we switch or not? And that's called Monty Hall paradox. Okay, and then how that would apply to the H1N1 virus, and even if you're taking a look at like the coronavirus, right? And looking at how the spread of coronavirus. And so here it gives you an example of the probability of positive tests with the H1N1 virus. So next we're going to take a look at how we would set up our tree diagram. And earlier you saw how we would have dependency looking at the conditional branches in determining the probability. So in this example, it shows you a probability tree for 2 main parts. So we want to have the branches, okay? And the probability of each branch is written on the branch, while the outcome is written at the end of the branch. Okay, so here I have 50%, right? 25% and 25%. That gives me a total of 100%. So the probability of each of the branch. Then the outcome of that would be this. So out of that 50%, 70% is the P and 30% will be the not positive, the 0.3. So when you go through, you would take this 0.7 and you would multiply it by the value from the probability from the previous branch, which is 0.5, which gives you 0.35 as the probability of having positive tests for branch A. Okay. as when we look at this one, we have 25% positive for branch B, which is at 25%. So you would take 0.25, multiply by 0.25, which gives you 0.625 as a probability for positive under branch B. So when you go from one level to the previous level, we would then multiply. When we're at the same level of hierarchy, we would add. Okay? So that's how you would be able to draw your tree diagram. So the probability tree show us how we would multiply or add the probability. We would multiply along the branches and add the probability down the columns. So we would add here and multiply along the branches. Okay. And that shows you some example on how we would look at the disease, the positive, the negative, and then the probability outcome. Okay, so before we get to Markov, here is the requirement for 9. You are to create a tree diagram for a TV manufacturing company to determine the probability of the random selection. A TV manufacturer has 3 factories, Site 1, Site 2, and Site 3, which produces 50%, 25%, and 25% respectively of televisions. 70% of the screen produced at Site 1 is LED. 25% of those produced in Site 2 is LED, and 25% of the television produced in Site 3 are LEDs. If the television produced by the manufacturer is selected at random, calculate the probability of that selection that will be LED. Okay. So we want to be able to create the diagram and show the calculation. And you can use box ones, or you can use line like this. And all you can do is you can insert, if you use Microsoft Word, right? And then you can do shapes, and then you can draw lines like that. Okay. Once you select that, you can choose, you know, if you wanted to make sure that the line looks different, you can do it that way, but you don't have to make it look different. Okay. So I have the first branch right here for Site 1, and I put that it's 0.5. Okay. Then the problem gave me that in the Site 1, 70% of the Site 1 production is LED. So I then draw another branch from Site 1, and that will be 0.7. That means that the 30% would be the other TV, right? Because we would take 1, subtract 0.7, which gives us 0.3. That will be the other TV, right? They add up to be 100%. Then I have the second branch, which is Site 2, and that's 25% of the TV production. And out of that 25%, another 25% is going to be LED. So we branch it under Site 2 with the 0.25% as LED. That means that we would have 0.75%, or I'm sorry, 75% that will be other TV. So 0.75 would represent other TV. Then for Site 3, this is shown in blue. Site 3 produced 25% of the TV. And of that 25%, another 25% will be LED. So that means that 75% is other TVs. Okay. So now as we see that we would total these up to be 100%, right? We add down the column and we multiply down the branch. So once you have the diagram, then you can start putting together the calculation. So let's make an assumption that there were 100 TVs produced by this company, right? We wanted to look at how many that would be for the LED production. So for site 1, the LED probability selection would be 0.7 times 0.5, 0.7 here, times the 0.5, which gives us 0.35. Okay. For site 2, we would take the 0.25, multiply it by 0.25, which gives us 0.625. That will be LED. And site 3, for the LED probability selection, that will be 0.25 times another 0.25, which also gives us 0.625. I'm sorry, 0.0625. Okay. So if they produce 100 TVs, then 35 of the TVs will be LED in site 1. Approximately 6 TVs that will be LED in site 2, and 6 TVs that will be in site 3 for selection. Okay. So you would have 35% chance of getting an LED if you pick from site 1, right? 6.25% to get an LED TV if you pick from site 2 or site 3. Any question? Question? So the diagram itself just help you visualize, right? The branching and the dependency from one event to another. Okay. Now, if I change the value for the production, the probability for the production of TV here, that would affect, right, the overall outcome of LED and the TVs. Okay. So for question 9, you can just include a diagram. You don't have to make it exactly like this, right? I've seen students draw it as boxes like what it's illustrated in the notes. Okay. But you have to solve by doing the multiplications of the probability down the branches. Okay, so before we talked about the extra credit, I want to touch on Markov. And I also included videos on this, so if you wanted to get a little deeper into it, you can also watch the tutorial videos. So Markov chain is, it shows us the transitions from one state to another according to the probability rules, okay? And it's often used in in illustrating finite system, okay, finite state, because there's that dependency in how we present a certain state. Okay, so for example, right, you have a brand new computer, nothing, just operating system, right? It's at a specific state. Then you start downloading a bunch of application and you install it. It changes your system to a different state, okay, after you did the installation, okay? So for the finite state machine or finite state automaton, right? This is it's just a model on how we would implement hardware and software that can be used to simulate sequential logic for computer programs. And it can be used to model problems, right? Look, like for artificial intelligence, for games, for different things. So a system input can cause specific changes that would represent as a system output in a finite state machine, right? Like if we were to use an example where we would have different input as in download files that's stored, it changes the state of the storage in the hardware. It also changes, it impacts the operating system as a software state. That's at the simplest level, of course. So now if we look at the dependency, right? In this example, if you ever seen the turnstile, which is the, at the bus stop or the, at the train station, if you ever ride the train station, you scan your card or put the coin into the slot, it rotates and it lets you in, right? So there's dependency from the coin being pushed to get the unlock, right? So this task, this execution doesn't occur until the previous task happens, okay? And this cannot be, the coin needs to be pushed in order to unlock and open up so the customer can enter, right? So it requires this coin to be pushed in. So the state of the system is reliant on, right, the first process, which then leads to the second process, and the second process cannot happen until the first process occurs. And here it goes and it talks a little bit about deterministic state, finite state machines, okay, compared to non-deterministic. So deterministic recognize, accept, right, languages that's regular, like binary strings in a specific pattern. And in Markov chain, we have the process that we talked about. The process that causes change over time is what's called stochastic. Okay. And when we look at the theory on how this is applied, we would see this applied to a lot of the things that we use every day. So here it gives you an additional example on how the process would be implemented, where you have random variable at a certain state, kind of like the bag of ball that we talked about. When you replace the ball in the bag, right, it creates a process, and this process satisfies the property of Markov theory, Markov chain. Now compare that to the next example, right? So we also have to think about how this would be time dependent. Okay, there are other factors that would be involved in this particular area when we're looking at state machines, is that what would be some of the time that would be the factor. So ultimately, I encourage you to read this, okay, because in some of the other upper classes, they would refer back to this, and you have to implement this as part of your programming piece for projects or various applications. But ultimately, what we've worked on is to really include the probability on how that would have dependency across from one state to another state. Okay, like in the example here, 0.3 is for A, and in order for that to move to the next, there would be another probability of this event happening from A to B, which then costs this probability for B to just having occur on its own. Okay. So by looking at this diagram, you would have 0.3, which is on the left here, multiplied by 0.7 because we're going down the branch, right? Plus 0.7 times 0.2, which gives us 0.35 as a probability. Okay. Now, solving exercise 10 is not required. It's optional, but I encourage you to take on the challenge and be able to solve it, okay? So think about Markov chain, think about how you would branch it, or you can implement matrices with this, okay? So if you decide to use matrix, you can type it into the solution or write it in and make sure that you present it so that way if you solve and you have the correct answer, then I will give you the points. Okay. So before we end, I just wanted to run through this. Now, it might be confusing, but if you map it out, right, or if you put it into matrix, it's going to help you. Okay. And then I'm going to come back to matrix in the future sessions, and we'll work on that. So this is about transitioning from one island to the other, right? So the visitor, they arrive at Honolulu, which is Maine, Oahu, and what they want to do is they wanted to go from Honolulu to Maui and Kauai, which is the adjacent island. And here it tells you that there's 70% of the tourists, they start at Oahu and they go to Maui. And then 20% of those would go to Kauai, right, from Oahu. And 10% stays on the same island. But from Maui, they would then continue to stay at 40%, or they have 50% that would go to Kauai and 10% would return back to the main island, which is Oahu. Okay. Then finally, from Kauai, they can stay there at 30% or go to Maui, and 40% will get back on Honolulu. So I tried to draw this out. If you wanted to make a diagram that's better for you to look at the steps, then you can. But what the question asks you is that if you start from Oahu, that's where everybody starts, what's the probability of the travelers that will be on the same island in the 3-day? Okay, I need to see a transitional matrix, a 1-step, and a 3-step transitional matrix. I've had students that turn in only one part, which gives them the partial extra credit. But if you are able to solve and give me both parts, right, not just the matrix, but solve it, right? Give me the percentage of the tourists that would stay on Oahu out of the 3 days. Okay. Then you get the complete extra credit points. I have a chat question before I end. Yeah, so you can use 100% as base to start. Or if it would be easier for you to apply a number, like you can make an assumption that, let's say you have 1,000 tourists to start with, how many of those? Because sometimes that might be easier for the student to kind of visualize it. But so give me the percentage that would answer the question and the matrices. Okay. All right. So when you submit your assignment, I'll look for number 10. If you solve number 10 correctly, I will add the extra credit points. If you don't do number 10, then there will just not be extra credit points added. So it's optional. Okay. Is there any question? All right. Type your name in the chat. Thank you for a good night. I will see you on Wednesday for lab. We will do lab this week with C++. Have a good night. Take care. Thank you. And Han, you won, so I'll send you the e-gift. Thank you. Have a good night. So I'll send it to your email, Han. Okay. You won the game from last week, I think, in the quizzes. Okay, everybody. Anybody have questions? If not, I'll sign off. Yeah, congratulations. I'm glad you won. $25 for Amazon, not bad. I haven't gotten a chance to purchase the e-gift card, but I will try to do that tonight. So you might see it tonight, tomorrow morning. Okay. All right. Take care. Good night. Bye.